All right, so we've done an example for transformations. Now, what we're going to do is we're going to do an example of applications of exponential functions. Particularly, what we're going to do is we're going to start with applications of exponential growth. We're going to be doing exponential growth and exponential decay separately. So for exponential growth, it might actually seem to be unimpressive at the beginning, but because the growth rate increases as the input grows, the function will eventually seem to explode or grow out of control. Now, this is something that is particularly surprising about exponential growth, and it's not something that really clicked for me until I had been studying exponential functions for a while. You'll learn eventually in calculus the true shocking rate of growth that exponential functions can exhibit. But it does take a while to truly understand why exponential functions are so special because of that growth rate. So for a function that does model exponential growth, typically we begin at small values. So I'll model that over here. So typically we begin at small values. And because we have small values, right, we have small output values here. Because we have small output values, the growth rate is pretty small. So we have a relatively flat curve here. But as soon as the output values start to grow and grow and grow, well, as the output values grow and grow and grow, then the growth rate also increases and increases and increases. And we get this sort of, this isn't really technical math vocabulary, but around this region we get what you could call the explosion zone. The explosion zone. So again, don't really use this in other courses. Nobody will know what you're talking about. This is really just my way of saying, hey, around this region, as the output values start to get large, so will the growth rate. And as the growth rate gets large, then the output values will increase at an even higher rate, and therefore the growth rate will also increase at an ever higher rate, and therefore the output values will increase at an ever higher rate, and therefore the growth rate will increase at an ever higher rate, and it just becomes this positive feedback loop where we get this unreal growth. It is way more impressive than any kind of growth you could get from polynomials of any degree. It is absolutely insane. And to illustrate this, typically what I do in an in-person class is I get students to take just a regular piece of paper. This is my fancy drawing of a piece of paper. Maybe it's got some writing on it or something. So just take a regular piece of paper and wonder out loud how many times you could fold this piece of paper in half. And typically students have in a grade 12 course, typically students have tried maybe something like this before. And you might know the answer is usually around 7. So if you're pretty good at paper folding, you can probably fold this piece of paper in half around 7 times, a regular piece of printer paper. The world record for folding a piece of paper in half is 13. Typically, if you ask some random person on the street, however, what the world record might be for folding a single piece of paper in half, they might guess a number higher than this. But this is the largest amount of times that somebody has folded a piece of paper in half, and you might consider that cheating even because it's not a regular piece of paper that they used. It was a pretty thin piece of paper that they used, and it was over a kilometer long. So the reason we're talking about paper folding here, if it's not clear, is that paper folding is an example of exponential growth. So let's say I have this piece of paper here, and this is a top-down view of this piece of paper. If I look at this piece of paper from the side, it's just going to look like a flat sheet, right? So that's the flat sheet of paper. If you fold it in half, then that flat sheet would have been folded in half like that. So it would be a little bit taller. And if you fold this in half again, then I actually don't know how to draw this. Will this be, oh yeah, hey, that's not bad. Then this is the flat sheet of paper folded in half again, so we can see that we go from uh, a stack of paper that is 1 sheet tall to a stack of paper that is 2 sheets tall, right? We have 2 sheets here after we folded it. And then we have a stack of paper that is 4 sheets tall here because we folded it in half again. And then I wouldn't know how to draw a piece of paper that is folded from a side view, folded in half again. But if we were to fold it in half again, it would be 8 sheets tall. And if we were to fold it in half again, it would be 16 sheets tall. And if we were to fold it in half again, it would then be 32 sheets tall. And if we were to fold it in half again, it would be 64 sheets tall, and so on. So this is an example of exponential growth because every time you fold this piece of paper in half, its height increases by a factor of 2, right? It doubles every time. So we have this doubling behavior. And we can only do this so many times before we start to get really, really large numbers, right? Fold it in half again, then you have something that is the size of a small novel, and then you have an even larger novel here, 256 pages, and then you have an even larger novel, 512 pages, and then you have a tome. You have a huge, huge, huge book, 1,024 pages in height if you fold it in half 10 times, which is pretty wild. So exponential growth is a pretty wild thing. Now, that truly doesn't speak to the insane nature of exponential growth, though, until you ask the question, okay, maybe I want to fold this piece of paper in half 103 times. So if you want to fold this piece of paper in half 103 times, you might say, okay, I expect this to be, I kind of understand exponential growth. I kind of understand that it will grow out of control and the stack of paper that I get will be incredibly high, incredibly tall. So I'm going to guess like 1,000,000 miles or something, or 1,000,000 kilometers, or 100,000 kilometers, or something like that. I would just guess some huge height. But if you were to actually fold a piece of regular printer paper, maybe it's a piece of printer paper that is incredibly large, but the thickness is still regular thickness for printer paper. If you were to do that 103 times, then that paper, that stack of paper that you would then have, would be as tall as the diameter of the observable universe, which is 93 billion light years in length, which is inconceivably tall. That sack of paper would then be inconceivably tall. To start to even approach an understanding of how tall this piece of paper would be after folding it in half 103 times, how tall that stack of paper would be. To get an idea of that, well, we should understand what a light year is. Light, first of all, is the fastest thing in the universe. It's inconceivably fast. Light travels at around 300,000 kilometers. This is a pretty far distance, right? 300,000 kilometers is an incredibly far distance. Light travels this distance every second. That is how fast light travels. And if you were to fold a piece of paper in half 103 times, that stack of paper, how tall would that stack of paper be? It would be so tall that it takes light, which travels at 300,000 kilometers per second, it takes light 93 billion years to travel from the bottom of that stack to the top. Or in other words, it takes over 7 times the current age of the universe for light, the fastest thing in the universe, to travel from the bottom of that stack of paper to the top after only folding it in half 103 times. That is inconceivable. Our brains can barely even approach an understanding of that kind of distance. And you get that kind of distance after only 103 foldings. That's what exponential growth is. It is inconceivably large once you get to even moderately large input values. So that is exponential growth. In the next video, hopefully I have illustrated how incredible this new function how incredible the growth of this new function is. And in this next video, we're going to look at a specific application for exponential growth, which is infectious diseases.